Oh, good morning. There we are. I don't see any students in Kingsport yet, but they're coming. And we're still missing a few over here as well. So, hi, David. How are you?
I'm good. You?
I'm doing well, thank you. It's good to see you over there. So, uh, they'll be coming in, I guess, here in a minute. So, yeah, right. So, okay. Um, While I'm waiting on the computer to fire up for me to write on and everything, let me go ahead and talk just a minute about a few things. One is we're not getting our tests back yet today, okay? I'm not quite finished with those yet, so we will get those back on Tuesday, all right? So that's thing number one. Secondly, we're moving on into Chapter 7. But one thing I want to make you aware of is you don't want to forget Chapter 6, okay? Now, I know in some classes you can move on to the next chapter and you can kind of push away what you have just worked on. Not in this class. The things in Chapter 6 are very much, they're just very basic to everything else we do. So if you are someone who is still struggling with the unit circle, struggling with identities, if you felt like you were struggling on the test, I advise you to still work on that material. Go back and get some help on that. Go over to the CFAA. They've got all kinds of a string of hours there. Email me, come see me, do something, get some help, okay? Work with each other. That's always a good thing too. But you will see as we start into Chapter 7 today, you will see that we still need that information from Chapter 6. So I just want to impress on you that if you felt like you didn't quite have that down, you want to work on that, okay? Sometime within the next week, I have to turn in early semester progress report grades. Some of you call them midterm grades. In my opinion, we're not quite at midterm yet, but we have to turn those in. So the grades I have for you will be coming from what you've done on My Math Lab and your unit circle quiz and that first test. Okay, so that's what it'll be based on. I want to say up front that because we're just a little ways in and we still have 2 more tests and a final, don't give up on me. If your grade's not where you want it to be right now, you still have plenty of time to get it there. Okay, so just keep working. But they tell us the deadline for me to turn in the grades is, I think, Monday. So I got to get those grades in by Monday. Okay, just based on what I have. Does anybody have any questions this morning? Go ahead. The My Math Lab quizzes are not due until the end of the semester. That is correct. And I will be opening up the ones for Chapter 7. Okay. What else? Anything else this morning? Yes.
How will the My Math Lab quiz grades affect our grade?
For the
I guess are they, each individual one, you have unlimited attempts, so you get, not full credit. Are you getting full credit for doing it?
You're getting the credit that you get on it. It takes your highest grade. That's what I'm going to see. I mean, I can look in and see how many times you've done it and the grade you got each time on the My Math Lab quizzes. I don't do that necessarily unless you have a question about something. But what I will see up front is the highest grade you got on any attempt that you did per quiz, and then the average of all those quiz highest attempts will be your My Math Lab quiz average. Okay. Is how that works. And the My Math Lab / unit circle quiz, anything else we do in class like that, homework quiz, all that goes together to form a grade that's the same as, counts the same as a test grade. Okay? All right, so just to, everybody's clear on the My Math Lab stuff. Hopefully, most of you have been working on that, I know, because I've been looking, but some of you are still thinking about working on it. Anything else this morning? Coming in thinking of some good questions here today. We're going to go over into Chapter 7 and start over there. It's about analytic trigonometry in Chapter 7. And we're going to be starting out by looking at inverse functions. So this morning, we're going to look at the inverse trig functions for sine, cosine, and tangent. And I will say that in this chapter, there will be some things later on that we'll want to use the calculator on. So I want you to start bringing a calculator, okay? Don't go out and buy something expensive. I think we said that at the beginning of the semester. Whatever you've got is probably fine. Just some sort of scientific calculator will do. If you have a graphing calculator already, that's fine. Just whatever you got, okay? Should be okay. If anybody has a question about it, you can ask me, okay? All right. Let me get logged in here. I'm not logged in. It did come up, though. So, and then we'll go into Chapter 7. Section 7.1 is a pretty big section, actually. It's kind of like back in Chapter 6, the one on, we had one in there, well, several in there that were pretty long. One was that Section 6.3. It was pretty long, but today we want to see what the inverse functions are, understand what they're doing, understand what they're asking when we have a question on those, see where they're defined, and talk a little bit about how to put them in our calculator. So if you have one today, you might want to go ahead and take it out. If not, you can work with it later. Make sure you can get these to work out. I'm going to give you some problems that involve the calculator to practice with, okay? And some that don't. All right. Let's see here. First off, inverse functions. We're going to have to talk a little bit about inverse functions. Does anybody remember what an inverse function is? Remember talking about inverses in some other math class? Probably an algebra class. I'm seeing a lot of it's too early looks out there. Is that what it is? So inverse functions have some certain properties, and these are actually somewhere in the first part of the book, in one of those chapters. As far as our textbook goes, they're covered in Pre-Cal 1. And I bet that when you hear some of them, you will remember. But in just a minute, this is just taking a little while to load this morning. I don't know what's going on, but in just a minute, we'll put up, what the inverse functions, how we write those out, and some of the properties of those to try to help you remember maybe some things that just you've probably seen before somewhere. What's a function while we're waiting here? What's a function?
It's like for every value of x, what y equals.
Okay, so when you put in x, you get out something for y. Okay, and also with the functions, one of the key things about those is that no x's can be repeated. No x values are repeated. If you put in an x value, there's only going to be one y value you get out, okay, of the function, like you're talking about plugging in x and getting out y. So this part right here is a little bit, we'll label it review. Hopefully it's review, but it may have been a while. I don't know. So, all right, so that's what functions are. No x values are repeated. Just that's a very basic definition, but it'll work for us. And we wanted to look at inverse functions, some of their properties. Now, functions, a lot of times we write them f or f of x. Inverse functions, we're going to write f with the little -1 up there, but that's not like x to the -1 where we say that's equal to 1 over x. This is just a notation for f inverse, or we might say f inverse of x, like that. It's usually how we will see those. So inverse functions, if two functions are inverses of each other, then one thing we know is that f of f inverse of x is equal to f inverse of f of x, and both those are equal to x. And some of you are really looking now like, whoa, this is too early. This is talking about composite functions. So let me veer off the path just a little bit and talk about composite functions. You all probably remember seeing composite functions as things like f of g of x, g of f of x. You remember seeing those things before somewhere? So that if you had, I'm going to take a little break over here on this side here. If you know that f of x equals 5x plus 3 and g of x equals 2x minus 1, and you want to know what f of g of 2 is, what does that mean for you to do? It's actually a set of directions telling you to do something. What's it telling you? Plug in 2 into which one? Yeah, in the g function. So g of 2 will be 2 times 2 minus 1. And we get that. That's 3. And then what do we do with that? Since that part's equal to 3.
Plug it into the x for f of x.
Yeah, so now we have f of 3. So that's 5 times 3 plus 3. So 18 is our answer for f of g of 2 on this one. That's what we're talking about with composite functions. So what I'm saying over here is if I have a function and its inverse, and I do the composite, whether I do f of f inverse of x or f inverse of f of x, I will get x out of both if they're inverses. Okay, if they are inverses. Another thing here is the domain of the function equals the range of the inverse. And the range of the function equals the domain of the inverse. That's true for all inverse functions. So it's like they swap out their x's and y's. That's what happens. Their x's and y's get swapped on their ordered pairs. Another thing about inverse functions is we've talked a little bit about symmetry, for even and odd functions. Inverse functions have symmetry also. Okay, they're symmetric about the line y equals x. Do y'all know what that line y equals x looks like? Yeah, so doing it from your direction. Okay, so the way you are facing here. It's where all the x's and y's are equal to each other. So it have points on it like 0, 0, 1, 1, 2, 2. All the x's and y's are equal. So let's see. F and f inverse are symmetric about y equals x. When we deal with these inverse functions, we look at a function that's 1 to 1 before we find its inverse. Okay, we are able to find the inverse of the functions, but we look at a function that is considered to be 1 to 1. So that's another thing we need to see what that means is 1 to 1 functions. In a 1 to 1 function, well, it's already a function, so we know that no x values are repeated, right? But no y's are repeated either if it's 1 to 1. So no x's or y's can be repeated is what that means. We've already established for it to be a function, no x's can be repeated. Also back over here with a function, do you remember that functions pass what test? If some
The pencil in the paper.
The pencil on the paper. Okay, I hadn't heard it called that, but yeah, that's what we do with it. What's it called? Vertical line test, right? But you're doing that, usually the pencil on the paper thing. So a function will pass a vertical line test, which means anywhere we place a vertical line, that's the pencil on the paper, right, on something we've graphed, okay, from whatever equation we're working with, that vertical line cannot pass through the graph of the equation more than once at any given place, okay, wherever we are. Now, with a 1 to 1 function, since no y's are repeated either, it still will have to pass the vertical line test because it's a function, but it will also have to pass the horizontal line test. Works the same way, except it's a horizontal line now. And we don't want it to cross whatever we've graphed more than once. I'll go back to our old standby, y equals x squared. It's a parabola. Is it a function? Yes, it's a function. Is it 1 to 1? Right, it's not 1 to 1. Okay. What about this one? Y equals x cubed. Is it a function? Is it 1 to 1? Yeah, so this one is a 1 to 1 function. Let's see, where do I want to go with that? I was thinking about something else here. All right, on that, let's go to one of our trig functions just a minute. Y equals sine x. Is it a function? Yes. Is it 1 to 1? No. It is a function. All the trig equations we work with, we've called them trig functions all along. They are trig functions. Okay. Are any of them 1 to 1? Think about the graphs for the other trig functions. What about cosine? The graph of y equals cosine x. Looks like this, but shifted over, it's not going to be 1 to 1 either. See how a horizontal line through there would cross it more than once? You all are seeing what I'm saying there with the horizontal line test? It's going to go through those waves in more than one point. What about the graph for y equals tangent x? Remember that one? Looks a lot like that y equals x cubed type graph, but it's repeated. So is it 1 to 1? No, because it's repeated. If it weren't repeated, it would be. But because we have it over and over again, then when we put a horizontal line through, we're crossing every time we're repeating that shape. Does that make sense there, how we're repeating? All right, what about the cosecant or the secant? Those graphs. They're not 1 to 1. Okay, none of the trig function graphs are 1 to 1. But we want to talk about inverse functions with them. So that's the deal here. We want to have 1 to 1 functions in order to talk about inverses. Okay, so what we do is we take a piece of these graphs. Now this piece that we're taking, we're going to limit the domain on what we just drew. For example, on this y equals sine x, we're going to limit that domain, so we'll have a 1 to 1 part of this graph to work with. Now, it's a good thing for us, I guess, that the way we limit the trig function graphs to make a piece that's 1 to 1 is kind of universally accepted. We can't all just choose. We'll all use the same parameters here. So to make this one 1 to 1, or to look at a 1 to 1 piece of it, we look at the graph just from negative pi halves to positive pi halves. So from here to here is the part we're going to look at to get y equals inverse sine x. We're going to look from negative pi halves to positive pi halves. There's my interval, including negative pi halves to pi halves. Now there's probably a much better picture than I can draw in the textbook here. I'll attempt to put in then the mirror image of this thing. Ooh, I don't know if I even want to attempt it here. I don't think I can do it. And my graph's not drawn so great. So what we'll do is we'll show it to you from the textbook. How's that? I think that'll work a whole lot better. So let me go over to the camera here just a minute. And we'll show it from there what the actual graph looks like. Let's see. Okay, I gotta get it in the right spot right there. All right, see this little drawing right here? That's where we're looking. Okay. On there's this reddish pink one is that piece of y equals sine x. They have it spread out a little bit more than mine was, so it's more strung out a little wider. And then the blue one, do you see how it's the mirror image over that line, y equals x? This is over on page 437 if you just want to note. Now, you're not going to have to graph the inverse functions for me. You are not going to have to graph them, okay? But I just want to kind of show you what's going on with these. We do want to know and understand what they mean if we have those out there. We want to be able to tell what the inverse sine is of some value. And we're going to talk about that here in just a minute. We also need to know that the inverse sine, we'll only be looking at it from negative pi halves to positive pi halves. But you will not have to duplicate the graph, okay? So if that's of any use for anybody's knowledge there, you might like to know that. So that's over on page 437 though, and it's just hard to draw those mirror images on this. Some of you are writing something down, so do I need to wait a minute here? Okay. We're good? We good on it so far? Okay. So what does all that mean? We want to look at that too. What does all that mean? We've said, you know, if we might have this, we've got it from negative pi halves to positive pi halves. What if I have an actual problem now? Okay. Before I put the problem up here, this is a backwards way of looking at things. We've talked about how in math we go backwards and forwards, right? Normally we go forwards first and then we go backwards. We'll square numbers and then we'll take square roots. That's like we do the forward operation and then we do the backwards operation. That's what we're doing here. We're going backwards. So if I have y equals the inverse sine of x, that is the same as saying x is equal to the sine of y. Okay, that's another way of writing. I mean, that's how we would clarify what's going on here. If y is the inverse sine of x, then that means that x is the sine of y. Now, we've been looking at problems that say things, you know, with the sine of something. So let's say the sine, and we'll make it easy, the sine of pi fourths, okay? The sine of pi fourths is equal to what? Square root of 2 over 2. So if I want to put it in that inverse form, what would I say then, according to what we've just written up here? I've got the sine of pi fourths equals square root of 2 over 2. How would I write that in an inverse form?
Would it still be square root of 2 over 2 since the y value and the x value are the same?
The y and the x are staying the same, but how am I going to write my statement? How am I going to write it in that form? Up there. Well, what's my y?
So square root of 2 over 2.
Well, the square root of 2 over 2 is my y. Wait a minute. Let's see. That's my y. That's my x, right? According to, is that what I've got written here? No, that's not what I've got written up here, is it? No, I didn't write it in the right format. Okay, so I've got the sine of y equals x right there, right? I wrote here x equals sine y, so here I've got x equals sine y. Correct? I'm just rewriting, putting the x on the other side. That's what I did. Instead of saying x equals sine y, I've got sine y equals x. Those mean the same. Will you agree? Okay. So if I want to write that then in the first form, in the red circled inverse function form, what am I going to write? Pi fourths is the y, right? Equals the inverse sine, square root of 2 over 2. The inverse sine of square root of 2 over 2 is equal to pi fourths. When we have this inverse trig function, remember math is like a foreign language, so we got to learn what it means. It's kind of a code for something else. Inverse sine of a value is asking us what angle has that value as its sine. That's what it's telling us. What angle has that value for its sine? Go ahead.
What is the pi over 2? What was that for?
These are our parameters. We'll come back to that in a minute. Right now we've not used that yet. We're going to use that here in a minute. That's where we're defining the inverse sine function, so that it's the piece we took off y equals sine x to have a one-to-one portion of the graph. What this part here means, though, is what angle has a sine value of square root of 2 over 2. That's what it's asking there. What angle has a sine value of square root of 2 over 2? Now that's actually where this negative pi halves to pi halves comes in, because not only are we asking what angle has that value as its sine, we want to know what angle from negative pi halves to positive pi halves has that. Okay? Because we can only go, you know, from here to here, according to the parameters that we set up. So when we say inverse sine of something, it's really asking this question that we've got up here. What angle has this as its sine? And we know that angle to be pi 4s. Does that make sense what we're asking there? What if I ask this then? Inverse sine of 1. What angle has 1 as its sine value? What angle from negative pi halves to positive pi halves, including those, has 1 as its sine value?
Be 90 degrees.
So pi halves. So here's another thing. We're always going to answer these in radians. Okay, so in this part here, we want to be in radians. When we do these things on a calculator, we want our calculator in radians. Okay. Later on, we'll change things on you a little bit. Okay. When we start working in the context of triangles, but for now, all we're going to focus on is radians. So even if we think degrees, we're going to have to switch it over. Okay, to radians. But this is correct because the sine of pi halves equals 1. And we're really just twisting that statement around is what we're looking at there. Does anybody have a question on that part right there? Let's try another one here. I'm just focusing on sine right now so we can get the concept in our head. What's going on? Let's do inverse sine square root of 3 over 2. I'm doing things we know from the good old unit circle. Inverse sine square root of 3 over 2. What angle between negative pi halves and positive pi halves has square root of 3 over 2 as its sine value? What's that going to be? Okay, is it pi 6? It's got to be pi thirds, okay, for the sine, the y value, okay? So it should be pi thirds. Okay, you are seeing the idea there? What angle, as its sine value, has negative 1/2? So inverse sine, negative 1/2. What's that going to be?
3
Okay.
pi halves.
I've heard 11 pi 6. I've heard 3 pi halves. I've heard...
Will there be 2 answers?
There won't be 2 answers. We'll talk about that, though, in a minute. Why is there not?
Are we supposed to memorize the entire unit circle going forward?
You should already know the entire unit circle, yes. Yeah, all of it. I mean, you know, if you know the first quadrant, you know it all, right? You just have to think about where things go. So you should know how to get all the values on that unit circle, what they are, okay? So we have to think about it a little bit more in this part here because we're thinking backwards. What angle has negative 1/2 as its sine? And I heard 11 pi 6, right? That's one thing I heard. But you're telling me negative pi 6. Why? We can't go all the way around, right? So you're at the right place when you say 11 pi 6. The problem with 11 pi 6, we have to get values between negative pi halves and positive pi halves. 11 pi 6 is a little bit bigger than that, isn't it? See what I'm saying? So, yeah, it seems a little strange, but we got to stay within these parameters. So, the angle that ends at the same place as 11 pi 6, we are now going to call negative pi 6 because that falls within the parameters of negative pi halves to positive pi halves. So it's going to be negative pi 6. In some ways, it makes it a little bit easier to think about because you already knew that pi 6 was the angle in the first quadrant that had a sine of 1/2, right? You already knew that. And so you're just going down below that in the fourth quadrant and getting that negative of that, negative pi 6. So in this part here, when we're doing the inverse functions, we're going to talk about values. Well, for the inverse sine from negative pi halves up here to positive pi halves, so we're looking at these values, right? We're only looking in quadrants 1 and 4 for the inverse sine. So we do want to get in our heads that that's going to go from negative pi halves to positive pi halves because of marking off that portion on the sine wave so that we would have a one-to-one function to work with there. We're asking backwards things. Okay, we're asking backwards things. All right, so we're getting it in our head a little better now. So inverse sine, negative square root of 2 over 2. What's that one going to be? Negative pi fourths. Good. And that's how we would want to answer that. Negative pi fourths. That is the angle from negative pi halves to positive pi halves that has negative square root of 2 over 2 as its sine value. Okay. Any questions so far about the backwards style we're working with today? All right. Let's look at the cosine, inverse cosine. Okay.
So you said earlier that anytime that you're taking a section of the graph, it's always going to be negative pi halves to pi halves.
On the sine graph, whenever we're doing the inverse functions, we'll take this section from negative pi halves to positive pi halves for the sine, okay? And we're about to do something different with the cosine. So let me put the cosine graph up here. Cosine graph looks something like this. Oh, gets worse and worse here. Cosine graph's doing something like this, right? Still period 2 pi. We see that. We see the amplitude is 1. This is, by the way, this is the cosine graph, so don't let me make you think that's the graph for the inverse cosine. This is the cosine graph. We're going to talk about the inverse cosine down here. But before we do, we need to section off a piece of this graph to make it one-to-one so that we can talk about the inverse. We see the graph is not one-to-one. It does not pass the horizontal line test. On this one, what happens if I go from negative pi halves to positive pi halves? Does that make a one-to-one part? No, it does not. Negative pi halves, it's right there, to positive pi halves, we would not have a one-to-one portion of this graph. So when this was decided, it was decided that for the cosine graph, to focus on that one-to-one portion, we would go from 0 to pi, where x is 0 to where x is pi. So it's that little portion right there. That's where the inverse cosine is going to be defined. Well, you don't have to think about the negative angles on this one. We won't be saying negative pi 6 this time. Okay. So what if I want to know the inverse cosine of square root of 3 over 2? Which angle has square root of 3 over 2 for its cosine, and the angle has to be between 0 and pi. I always get both answers, pi thirds, pi sixths. It's a toss-up, right? All right, the cosine has to be square root of 3 over 2. So the cosine's square root of 3 over 2 is going out further on the x-axis and then just going up 1/2 on the y-axis, right? So out further, but up less. Which one's that? You want to take another shot at it?
Pi sixth.
It's pi sixth, right? It's pi sixth. So on your unit circle, if you're using that, if you've got that in front of you, where it's pi sixth, you should have the coordinates square root of 3 over 2, 1/2. Do you? You have those coordinates? Okay. Just making sure there. What about inverse cosine of 0? What angle from 0 to pi has 0 as its cosine? I heard 0. What else? Somebody else wants to say something? What? Pi over 2. Same as 90 degrees, but we want radians. What's that? Could it be negative pi halves? That's a good question because, you know, the cosine is 0 at negative pi halves, right? It can't be negative pi halves, though. Why?
Because you can't go into negative on cosine.
On the inverse cosine, we're only looking from 0 to pi. Okay, we always have to stick in those parameters. Otherwise, we could always have two answers for about most any of these, couldn't we? You know, when we look for where the cosine was square root of 3 over 2, well, the cosine square root of 3 over 2 for an angle in the first quadrant and the fourth quadrant, correct? But we're only defining these in certain areas. On the inverse cosine, we're only looking from 0 to pi. So that will only give us one answer for this. What about something negative? Inverse cosine of negative 1/2. What angle from 0 to pi has a cosine value of negative 1/2? That's what that question's really asking you. What is it? Pi over 3? Pi over 3 has a positive 1/2 cosine, right?
The 2 pi over 3.
2 pi over 3. How about 2 pi over 3? Coordinates at 2 pi thirds or what?
It's negative.
Negative 1/2, right?
1/2 over square root of 3 over 2.
Negative 1/2 positive square root of 3 over 2 are the coordinates at 2 pi thirds. And that is what we're looking at there. Okay. This requires a lot of thought, doesn't it, this part? Do we still need our unit circle information? Most definitely. Okay, definitely. So we want to stay on this. Let's see. Where do we want to go with this part now? Let's go to y equals inverse tangent x. And I'm just going to tell you on this one. I'm not going to draw it, okay? But we're still going to define it from negative pi halves to pi halves like we did the inverse sine. So it's at least something like something else with one difference. There's the difference. I'm putting parentheses instead of brackets. Why?
Because it can't include pi halves.
Why can't it include pi halves and negative pi halves?
Because it's undefined.
It's undefined. Tangent is undefined at negative pi halves and positive pi halves. So we're not going to include those values, but it's going to be the things in between. So that basically, if I'm thinking about my unit circle here, now I'm thinking about my quadrants and, you know, where the values are, whatever signs they might be. First off, I'm looking, you know, I know I'm looking quite a bit from 0 to pi for the cosine. I'm looking from negative pi halves to positive pi halves now for the inverse sine and the inverse tangent. I just have to remember that at those endpoints, the inverse tangent's undefined. Okay, we don't use those. I'm sorry? We don't use at negative pi halves and positive pi halves because, yeah, we don't use brackets. Brackets show inclusion, and we're not including those values because the tangent at those values is undefined. Okay, tangent's undefined. All right, so here's what we're knowing so far. If we're looking for an inverse sine value, we're looking in these two quadrants, right? Inverse sine was negative pi halves to positive pi halves. We just said inverse tangents, the same thing, except we won't use the negative pi halves and positive pi halves themselves. So that part you can keep together, because they're in the same places. Inverse cosine, we said, was from 0 to pi, so it's going to come up in one of these areas. You're going to be looking in the first and second quadrants for inverse cosine. Nothing in the third quadrant. Now, each time we're looking for these inverse function values, it's giving you an option to find the value if you have a positive value or a negative value. You see what I'm saying? If you are looking for the inverse cosine of square root of 2 over 2, you're up in the first quadrant, right? Inverse cosine of square root of 2 over 2, you're here in the first quadrant because you're looking for an angle that has a positive cosine. Cosine's only defined in these two. If it was the inverse cosine of negative square root of 2 over 2, you're in the second quadrant. That's where you've got negative cosines in the part that it's defined for. If I don't have it labeled up here that it's defined in that part, then we're not interested in it right now. Okay. Inverse sine, if we have inverse sine of something positive, we're going to be in the first quadrant. Inverse sine of something negative, we're going to be down in the fourth quadrant. Same with the inverse tangents. It gives us an option for everything, but we're only going to get one value back because we're only defined in two quadrants. It's a little different to think about there. Tangents probably, I don't know, maybe even more thought-provoking. Because remember, your tangent's your y over x. So what's the inverse tangent of 1? Also notice, anytime we write these up, inverse trig function of a value, what kind of things are our answer? All the answers we're getting are, how would you describe them? We're getting things like pi 6, pi halves, 2 pi thirds, negative pi fourths. What are all those?
They're fractions.
Pi halves. Okay, they might be fractions, but that's not what I'm looking for, but you're right. I didn't get that one.
Radians?
They're what? They're in radians, which means they are, what do we measure in radians? Angles. Okay? So they're all angles. Whenever you do the inverse trig function of some value, your answer is an angle. Now, before now, in chapter 6, that's where we've been before now, we were doing the trig function of an angle and getting one of those coordinates, right? The trig function of an angle gives us the coordinate. Now we're doing the inverse trig function of the coordinate, and our answer is the angle. So anytime you do the inverse trig function, your answer is going to be an angle. We good on that? Pretty good. Let's go back here to this part. The inverse tangent of 1. What is it? Pi over 4. You got it. That's good. Pi over 4 is the angle that has a tangent of 1. This is why the tangent of pi fourths equals to 1. Pi fourths, what are our coordinates?
Square root of 2 over 2 and square root of 2 over 2.
Right, so they have to be the same in order for the tangent to equal 1. Correct? So that's where we get 1 for the tangent at pi fourths. Let's make it a little tougher. Now, if the inverse tangent is square root of 3, that it's going to be either that pi over 6 or pi over 3 angle. You might not know which one right off the top of your head, but figure it out real quick. Okay? Figure it out. Put the y over the x and see which one it's going to be.
Maybe 5 or 6.
Let me give just a minute, okay, for everybody to check it out. See which of those, pi 6 or pi thirds. Here's pi 6. You've got coordinates there. Here's pi thirds. What's my coordinates at pi 6?
Square root of 3 over 2 for x and 1/2 for y. So it'd be pi over 6.
Does everybody agree? Do you agree? No, I see some disagreement. So what are we going to do when we can't agree in here? I don't know. To flip a coin, I guess. All right. You're putting the y over the x, right? Tangent's equal to y over x. So, okay, so let's go down here. Tangent of pi 6 equals 1/2 over square root of 3 over 2, which is 1 over the square root of 3. And if I rationalize, I get square root of 3 over 3. So it is not pi 6. Tangent pi thirds will be the y over the x. So I get square root of 3 over 1 when I cancel those 2's, which is just square root of 3. The answer here is pi thirds. Okay. And again, you don't have to memorize that. You can work those out. Put the y over the x and see. But you know if it's got a square root of 3 in it, it's going to go with one of those two angles. Pi 6, pi thirds, one of those. That's a good starting point at least. Tangent's a little tougher maybe to think about. Yeah. No, we've not done cotangent yet, so don't go there just yet. Okay. All right. Questions so far on what this means when we say the inverse function of a value. We're interpreting that as which angle has this as its trig function value. Which angle within the set parameters has this as its trig function value. That's what we're asking on these. So I told you there would be some calculator problems in here. Let me talk about those just a minute. Even though I know most everybody says, well, I know how to punch things in a calculator, but let's make sure. Okay, I'd feel better if we make sure. Most of you know on your calculator you have a cosine key, you have a sine key, and so forth. Above the cosine is where you normally see inverse cosine. Is that where you see it on yours? Most of you. What does it mean if something's written above the key on the calculator?
You hit the second key and then it'll work.
You've got to hit the second function key. It usually says second like that, and it will work. Okay, for whatever's written above the normal key, I guess we could say. Above whatever's written on the key. All right, so if I'm doing, let me get one out of the textbook here so you can kind of check it out. This is number 26 off of page 446. And I have the inverse cosine of 0.6. Then I'm going to punch in my calculator. In most calculators, you're going to punch it this way. Second cosine, because you're trying to get that inverse cosine. And then you're going to put in 0.6 and equals or enter if you're on a graphing calculator. What mode should your calculator be in here? Radians. Yeah, remember we said at the beginning, today, put your calculator in radians. We are working in radians right now. It will make a difference what your answer is. So if you have your calculator, punch that in, make sure your calculator's in radians, and we'll see if we've got some agreement here. You all have this stuff, like I know most of you have those cell phone calculators as well. I don't want you to use those on a test, but if you want to check out how that works with this, if you turn your phone sideways, you know you get all the extra stuff. And so you've got that inverse cosine on there. It works a little different on those. I mean, as far as how you punch it in, I don't think you punch it in this way. You might actually have to do the 0.6 first and then tell it to do the inverse, which is a little bit different. More backwards with the backwards. What are you getting for this one up here, though? Anybody done it? Anybody punched it in? 0.927. Okay, so 0.927, that sounds right. Saying what angle has a cosine of 0.6, and it's the angle at 0.927 radians. Almost 1 radian, not quite. Okay. We haven't done a lot of work in here with calculators yet. In fact, we skipped a part back in the first, in chapter 6, that worked with calculators, and I'm going to have you go back to that and practice some as well. It's over on page 376. This is how we're punching in the inverse functions as far as putting them in the calculator. We've got to use that second function key in some way to get those in there, okay? Let me go back over. Does anybody have a question about this one first before I move back? Yes?
For our answers, do you want us to just leave the 0.937, or do you want us to try and convert it into something pi over?
No, on this you would just leave it. I would probably tell you to round it to 2 decimal places, so we'd put 0.93 is probably how it's going to be for that, okay? You would just leave it. And this is an approximated answer, whereas everything we've worked with so far has been exact answers. Now, here's the clincher. If it is asking you something, inverse trig off of your unit circle, you know, if it's inverse trig function involving a square root of 3 over 2, 1/2, square root of 2 over 2, a 0, a 1, a negative, negatives of any of those things, then I would expect those answers to be exact because we know them from the unit circle. So, you know, I want you to say the angle's pi fourths or the angle's pi sixth. If it's something off the unit circle, we know which values are from there. We did not work with a 0.6 value, though, off the unit circle, right? Y'all seeing the difference? Normally in the textbook, the way they tell you that is they'll say find the exact value of each expression. You know, on the test, I put find the exact value, and it was things from the unit circle. Everything on the test was exact values, except some of you decided to do some division and give me decimals. I didn't need that, okay? I said you could leave it in terms of pi. I wasn't trying to make it harder for you, okay? But exact values are actually just easier to work with, I think. All right, so back over on page 376, that was back in, I don't know, section 6.2. There was some calculator work back there, and we skipped it. But here's the deal with it. Like on number 66 there, it's going to ask you for the cosine of 14 degrees. When you see that, your mode's going to have to be in degrees because that's what it's telling you. Everything we work with, though, in Chapter 7 on the inverse functions will be in radians. In this part right here, where we're going back just to get our calculators up to speed, I guess we could say, you'll have to pay attention to whether it's degrees or radians, okay? So cosine 14 degrees, when you put that in, you should get 0.97, okay? Approximately equal to, that's my little squiggly equals, approximately equal to. Then if you see something like the sine of pi eighths, your mode has to switch now to radians. Make sure you know how to switch modes. If you don't know how, show it to me after class or ask me and I'll do it for you, show you how, okay? Or try at least. Sine of pi eighths, you're going to put that in like this. Usually on your calculator when you punch sine, it comes up with parentheses normally. You're going to put in pi divided by 8. You've got a key on there that says pi. Use that pi key if you have that. Okay. So what do you get for that one? Did anybody get it?
0.382.
Okay, so I'll round to 2 places and get 0.38. I'm just putting these up here so that if you're not doing them now, you can check them later. You'll have some in the textbook to practice with. So the odd ones have the answers. Please do check and make sure you're punching things in correctly. Now the bigger thing from this part back here is one like 72, where it tells you, and I'll leave it in radians for now, cosecant of 5 pi 13ths. And so you go on your calculator to do the cosecant of 5 pi 13ths. And what's the problem? Does anybody see a problem about doing the cosecant? You don't have a key for that. That's right. There is no key for cosecant. There is no key for secant or cotangent either. All you get is sine, cosine, and tangent. You're going to do 1 over what? 1 over the sine, not the inverse sine. Just 1. Remember, 1 over sine is equal to cosecant, right? So be careful now that we're studying these inverse things. The inverse doesn't mean that we're putting it down under something there, okay? In this part, that's not what we're looking at. So 1 over the sine, like our identity said, is still equal to the cosecant. So on our calculator, we're going to say 1 divided by the sine 5 pi divided by 13, close parentheses, equals. Now I'm writing this out, these steps for the calculator, because if you miss some parentheses, you know, things are going to get screwed up on there. And we're trying to think like the calculator when we put these in. So that's our new thing. We're going to think like a calculator now. Okay. What are you getting for this one? 1.07. That's what they got too. Okay, I'm using the textbook answers here. That's what they got also. Were you able to get it? Okay. You want to practice with those just to make sure we can get in the swing of knowing what to do with those. I want you to be able to use your technology when you need it there. We just didn't need it in Chapter 6. Any questions on what's up here right now? All right. Remember when I said f of f inverse of x equals, this was the part that y'all said it was too early for. Remember that property right there? We're going to use that property just a minute. Let's put up here the inverse cosine of the cosine of pi thirds. Okay, we're just going to think about that thing a minute up there. We'll leave that hanging up there. But inverse cosine of the cosine of pi thirds, what would I do first?
You do the cosine of pi thirds.
Right, you do what's in the parentheses, the cosine of pi thirds. Just like any operation, you're going to go to the innermost part first and work out. What is the cosine of pi thirds? 1/2. Good. We're doing a good unit circle review today, aren't we? So that means then I've got to bring this down now. The cosine of pi thirds was the 1/2. I have not done anything yet with the inverse cosine. But now the rest of my problem would say, what's the inverse cosine of 1/2?
Pi thirds.
Pi thirds. I just went in a circle, didn't I? The inverse cosine of the cosine of pi thirds. Well, we said up here at the top, that would be this illustration right here. F inverse of f of x, I started with the inverse of the function, right, is equal to x, whatever was there. It's almost like, I hesitate to say this, but it's almost like the inverse and the function are, you know, they're undoing each other. That's what they're doing. It's like if we have the square root of x squared, the square root and the squared are undoing each other and you just get x. Here it's like the inverse and the function are undoing each other and we just get the argument. As long as the argument is within those parameters we've already talked about. So this was an inverse cosine. So as long as whatever's in that argument spot is between 0 and pi, it would be our answer. What if it isn't? Then we would have to find an angle that is within the parameters that has that same value. That same cosine value we're looking for. So this one, it looks like that part just comes out. The argument just comes out is what it appears to happen. What about this one here? We have the inverse tangent of the tangent of -2 pi thirds. Now, judging from what we just saw, we are all wanting to say the answer is -2 pi thirds. Is that correct? That's what we're wanting to say? Based on the previous example, I think that's what you'd want to say. There's -2 pi thirds, right? Problem is, inverse tangent is only defined where? Negative pi halves and pi halves. We need that whole quadrant, okay? So negative pi halves up to positive pi halves is where the inverse tangent's defined. And this is not in that range, is it? No, it's outside of that. So what we need to answer here with is we need an angle. Need an angle. Whoops, I can't spell angle today. That's from negative pi halves to positive pi halves with the same tangent as negative 2 pi thirds. Since we were talking about the negative 2 pi thirds angle, but it's outside the range of the values we can use, we need an angle that's inside the range of values we can use that has the same tangent value. What angle would that be? It'd just be pi thirds, wouldn't it? Up in the first quadrant. Pi thirds, the one that kind of hooks onto this in a way, if we just go on through. Pi thirds is going to have the same tangent value as negative 2 pi thirds, isn't it? The angles in the first quadrant have the positive x and positive y, giving us a positive tangent. The angles down here in the third quadrant, where that negative 2 pi thirds is, they have a negative sine and a negative cosine, giving us a positive tangent. They have the same coordinates here as far as the values go. So our answer for this one's going to be pi thirds. We need something that's within the prescribed parameters that has the same value as whatever that is they've got in there that's outside of the range. Negative 2 pi thirds was out of range. Is it true that the tangent for negative 2 pi thirds is the same as the tangent for pi thirds?
Yeah.
Think of your coordinates. Coordinates for pi thirds are 1/2 square root of 3 over 2. The coordinates for negative 2 pi thirds are negative 1/2 negative square root of 3 over 2. So the tangents end up being the same. We're doing a lot of thought-provoking things in this first section. A lot to think about here. I'm giving you a lot to think about over the weekend. All right. Let's try one more like this, because this is, I don't know, a lot of thought here, I think. How about the inverse sine of the sine of 9 pi eighths? And where's 9 pi eighths going to be? In which quadrant is that going to have the terminal side? Nine pi eighths is going to end up where? Third quadrant, good. Because it's 1 1/8 pi. Okay. We don't even know anything about the coordinates for 9 pi eighths. It's not on our unit circle. But what we do know is that it is not from negative pi halves to positive pi halves. We know that much, right? We need an angle that's going to have the same sine value now as 9 pi eighths. What kind of sine value does 9 pi eighths have? Positive or negative? It's negative. Okay. So this time I don't want to jump up in the first quadrant. I need an angle that has a negative sine value that would be the same overall value, though, as 9 pi eighths. So I'm going to find that down in this quadrant, in the fourth quadrant. Okay. So if this is all that, goes around to 9 pi eighths, what's my little angle here going to be? Negative pi eighths. Because pi, if I went all the way around to pi, that was 1 pi, and then this little section here was pi eighths more. So we've got symmetry going on here, right? We've got symmetry to get those same values. So this is going to be negative pi eighths, because that is out of the range of negative pi halves and pi halves. What about the inverse sine of the sine of negative 3 pi sevenths? What do you think? Can we just say negative 3 pi sevenths, or do we need to find something else?
You should be good because you're just under negative pi halves.
We're just under negative pi halves at negative 3 pi sevenths. That's correct. So negative 3 pi sevenths is what we get there. That's the kind we really like. It's where we can just take the argument and put it out there as the answer. Negative 3 pi sevenths is between negative pi halves and positive pi halves. If you're not sure, convert negative 3 pi sevenths and negative pi halves both to 14ths with a common denominator so that you can compare those. Okay. Negative 3 pi sevenths. Well, it'd have to be a 3.5 over 7 to get the 1/2 in front of the pi, wouldn't it? See that? So maybe you can think about it that way. That's why you said it's just under that. So it's within the parameters that we've set up here. Any questions there? That's a lot to think about, isn't it? I'm going to give you some problems to practice on. I want you to practice on these, okay? Section 6.2, going backwards. These are calculator problems, but do go back and practice and make sure you can do them because they'll help some things we do later on make some sense in this chapter. We're going to look at 65 to 75 odd. I want you to look at those. Section 7.1 on 446. I want you to look at, practice with, do 13 through 43. Odd there. We're not completely finished with section 1. Like I say, there's a lot of stuff in section 1 here. We still have to solve some equations with inverses. We have to find some inverses. Okay, things to do here. We'll work on those on Tuesday. I'll also give your test back on Tuesday. Does anybody have any questions today about what we're doing? You'll want to work on this stuff soon before you forget it. Believe me, okay? If you wait till Sunday night, Monday, I'm afraid you might have forgotten this by then. Then you'll have to replay the video, and it'll take more time to remember. Work on it soon. Any questions? All right. You'll have a great day then, okay? David's lonely over there today.